The following is a selected video from masterthecontent.com, where you will find an extensive video library of lectures for a variety of standardized admission tests. We offer over 600 hours of detailed video lectures for a multitude of standardized tests. Use our interactive in-lecture table of contents to find specific topics of interest. Work through numerous in-lecture examples to help you internalize concepts. To learn more, visit masterthecontent.com. Your career, our passion.
This is very, very important for you to understand, as it will help you immensely. We see here, first of all, this right here is the solid phase. Just go ahead and point that out. This right here is going to be our liquid phase. This here is going to be our gas phase. Perfect. Okay, well, let's actually go ahead and take a look at what's taking place here. As we go up our curve, we see that the H2O is solid and it is being heated. And therefore, because it is being heated, we also see that there's a temperature change taking place. And if we want to calculate the amount of energy that it takes to either cool or heat the solid right here, we can basically use this equation here. And our specific heat value is given to us as well. Great. Perfect. Now, when we're at this phase right here, what's happening is that the solid and liquid are in equilibrium. And because they're in equilibrium and it's going to be a phase change taking place. Remember, this is where it's going to be the energy required to go from solid to liquid. We can just use our latent heat equation that we had, where it's mass times mass times the heat of fusion. And again, there's a phase change taking place here. Wonderful. Now here we're at 0 degrees Celsius, because that's the melting point of water, and we're going all the way up to 100 degrees Celsius. And that H2O is in the liquid phase there, and as we travel up, we're basically, it's being heated. And there is a temperature change taking place here. And again, if we need to calculate the energy to either heat or cool that liquid, we can just use our equation here. And oh, this value is actually incorrect. Let me just go ahead and write that in for us. It's going to be 4. Let me just rewrite that just a little clearer for us. Right, it's going to be 4.184. Okay, great. At this point now, we're going to be at 100 degrees Celsius. There's going to be another phase change that takes place. And that phase change is going to be liquid to gas. But liquid and gas here are in equilibrium. So the liquid is going to be boiling, the phase change takes place, and here the intermolecular forces, just switch colors here. So here the intermolecular forces are going to be weakening. And again, to calculate the amount of energy required, we could just call upon the mass times heat of vaporization equation, where the heat of vaporization, as we just saw, was 2,258 joules per gram. Wonderful. At this point, right here, the gas is now going to start being heated, right? And there's going to be no more intermolecular forces. Okay, great. So again, there is a temperature change taking place, and the energy needed to change that temperature to either heat or cool the gas, we can just use this equation here. Excuse me. So now let's actually take a look at an example where we go from our solid state into the gas phase, and let's see how we would calculate the amount of energy needed to transition throughout the heating curve. Okay, great. Let's move on to our next slide. Here we're actually being asked, what is the total amount of energy required to heat a 50-gram sample of ice to 110 degrees Celsius from negative 10 degrees Celsius? So let's look back at our heating curve for a second. All right, and let's see how many steps we're going to have to go through. So if we're at negative 10 degrees Celsius, that means we're solid, and it's going to be one phase to go to 0 degrees Celsius right here. Then we're going to have to go through a phase change right there, and then we're going to have to, from 0 degrees to 100 degrees, we're going to have to heat that liquid. Then we're going to have to go through another phase change right there, and then we're going to have to heat that gas from 100 degrees Celsius to 110 degrees Celsius. So there's going to be 5 steps that take place. And what you do is, once you find the energy for each one of these steps, you add that energy up, and then that's how you would find the total amount of energy required to go from, I think we were negative 10 degrees Celsius to 110 degrees Celsius. Let's go ahead and do that now. Wonderful. Okay, for the first step, we can just use the energy equation that was given to us, where it's just the mass times the specific heat and the change in temperature. The mass we have here is 50 grams, and the specific heat that was given to us was 2.03 joules per gram degrees Celsius. And we're going to 0 degrees Celsius. All right, so we're at negative 10 degrees Celsius. Perfect. Once we go ahead and we actually equate this, we're going to end up with a value of 1,015 joules. Okay, great. Let's go back to our heating curve for just a second. So we were about here, and now we're here. And to go from here to here, we're going to have